Any questions from the previous discussion?
No, sir.
So we were looking at the properties of quaternion. Where did we reach? Did we discuss about multiplication?
Sir, I think we only did it ijk multiplication, like ij into jk. This part only.
This one, these two
Yes.
things.
Yes,
Yes, very good. So addition is adding the components. Simple. Quaternion is a set of 4 numbers, which has some special set of operations which we are trying to define, similar to the complex numbers. So the equality of two complex numbers would be the case whenever the components are equal. And how do you add the quaternions? You simply add the components of them. And then the negative of the quaternion is simply negating all the components of the quaternion. And for multiplication, we have to use these special rules because we had indicated that the quaternion q is nothing but q0 plus iq1 plus jq2 plus kq3. So if it is that, which is similar to complex numbers where we had only one complex quantity, that is a plus ib. So the special definitions for this I and j and k are these. That is I square equals to j square equals to k square equals to ijk equals to -1. And then we also indicated how one can show that ij equals to k and k equals to minus ji. So this itself shows that quaternion multiplication is not. This is from the given rules, okay? It's not commutative. Multiplication is not commutative. Similarly, all other interactions between the I and j are defined as given in the second bullet. So you should observe that.
Sir?
Yes.
Sir, that second part of the equation, like k equal to minus ji, how do you prove that, sir?
Did we not attempt that?
Sir, we only took the first part, ij equal to k. So now it is fine, sir.
Sir, you're mute. Sir, you're muted, sir.
Sir, you are on mute, sir.
Sorry. If you look at the right hand side, that is where I have discussed that ijk equals to -1 is the basic assumption we make. And then you multiply on the left hand side by j in I. So we already are using the associative law for multiplication, where we open up this braces and then we get j into I jk equals to minus ji on the right hand side. And then we are also using, one of you already indicated the multiplication, that is multiplication by a scalar is commutative. That is, that property we are already using it. That is, this is -1 is on the right hand side. So if you multiply it on the left by ji, it should be actually ji into -1. But that we have taken it as minus ji. That means when a scalar quantity is multiplying the ijk vectors, it commutes. That property we are already using. One of the indication we gave was similar to the matrices. In the matrices also we have been using that. But here that is one of the law assumptions we already make. I think the right hand side clearly, then you have j into I, jk equals to minus ji. So I into I will become -1. So once again, we allow that -1 to come to the left hand side. And then minus j square k equals to minus j. But j square itself is -1. So -1 into -1 is +1. So you get k equals to minus j. This is one way to show. Okay. You may have alternate ways to show. You can try it out. Is this okay?
Yes, sir.
Yeah, but thanks for the question. So similarly, you have to show other things. So some of them I will ask in the quiz. So you can go back and work it out. Observe that the derived rules are related to cross product. You know that I cross j is actually k in your three-dimensional system. If I and j and k were assumed to be unit vectors in the direction of x, y, z axis, orthogonal axis, then I cross j is k and minus j cross I is k. This we already know. So you can already see some geometric properties of the three-dimensional spaces are already captured by this ijk vectors and the way in which we have defined the interactions between ijk. Okay. Any questions here? This observation, are you able to notice it? K cross I is j, even in the three-dimensional space. You had hinted this indication that ijk can be thought of as 100, 010, and 001. Clearly, multiplication is not commutative. Ij is not equals to ij is not equals to ji. Let us multiply now two generic quaternions. So if you have p equals to p naught plus ip1 plus jp2 plus kp3, and similarly q equals to q naught plus iq1 plus jq2 plus kq3. So how do you multiply it? So we can use the usual distributive rules to compute the p and q. That is the scalar quantity. First p naught will multiply everything. Then ip1 will multiply everything on the right hand, that q vector, or okay, q quarter. So this is what we obtain. This is the expression we have: p naught plus ip1 plus jp2 plus kp3 multiplied by this one. So p naught multiplies everything, ip1 multiplies everything on the right second term, jp2 multiplies everything, and similarly kp3. So if you expand that, this is what we get: p naught into q naught, ip1 into iq1, sorry, p naught into iq1, p naught into jq2, p naught into kq3. Similarly, ip1 should multiply everything else. So when ip1 multiplies everything on the q quaternion q, you obtain this expression. Similarly, jp2, similarly kp3. Now let us try to simplify this. Let us look at this. The easiest simplification we obtain is this I square thing. You have I square, j square, k square. We already know it is -1. So you can notice that along the diagonal here, this is not really a diagonal. This is just to indicate. So what you have is minus p1 q1 minus p2 q2 minus p3 q3. These are all scalar quantities. Everything else, if you observe, they are all having coefficients either I or j or k, or combinations of them, which will ultimately lead to one of the coefficients I or j or k. So the scalar quantities are exactly the ones whose coefficients are I square, or from I square, j square, or k square, or the standard constant p naught to q naught. So that is the first simplification we obtain. The second simplification, you can notice that p naught is multiplying the q vector, that is q1, q2, q3. P naught multiplied by iq1 plus kq2 plus jq2 plus kq3. Similarly, if you look at this vertical location, q naught multiplies ip1 plus jp2 plus kp3. P naught multiply something, Q naught multiply something, and then the rest of the terms are the combinations. That is Ij is nothing but K. So this will become K times P1 Q2. Similarly, other quantities. So let us see how to interpret them. So we have already indicated that the quaternion P can be thought of as P naught plus vector part of P, Q naught plus vector part of Q. So what would be this expression now? The first term P naught minus, is it a dot product of
P
vector
dot
part
Q.
of P and Q?
Yes, sir.
Very good. So that's what we will indicate. And what about this last row?
This cross product.
Excellent. So it is a cross product of vector part of P with vector part of Q. So that is what it is. What does the last line simplify to? This one. So okay, I will just go one step back here. So P naught multiplying the vector part of Q, Q naught multiplying vector part of P, and you have vector part of P cross vector part of Q, and above you have P naught Q naught minus vector part of P dot vector part of Q. So if you remember this, this will give you a clue how to compute the quaternion multiplication. Of course, simplification is always required when you have numericals. It is clear that whatever you obtain is also a quaternion, so they are closed under multiplication. So where does the non-commutativity property come from this expression? Can you tell?
Cross product.
If we replace Q by P, then we'll get the same expression.
No, the cross product is not
Cross
commutative.
product is cross product.
Cross product is not commutative. Even if you replace P and Q by each other, what you obtain is Q cross P, but that is not same as P cross Q. But every other quantity, there is no other issue, no issue. Here you have P naught Q, it will become Q naught P and P naught Q. So it's same as whatever we already have. And dot product is commutative, symmetric. So there is no issue there. So the first three terms or first four terms are commutative. Only the last term has a trouble. So of course, the cross product is the one which is causing the non-commutativity property. But will it cause difficulty in computing the inverse? We have to see. So cross product is not commutative. So okay, so this one, can you immediately try it out? Give one numerical quickly. Try out and let me know the answer now. I have two quaternions. Try to compute the product now.
Sir, you are muted, sir.
Yeah. Yes, I am here.
Sir, for P into Q, it is 8 plus 7i, sorry, 8 minus 9i minus 2j plus 11k.
I think minus 6j. So sorry, minus 2j. Sir. Minus 2j.
Yes, sir.
Sir, you are on mute if you're speaking something.
Oh, sorry. Yeah, it is 2j. So any questions until now? If you are given two quaternions, will you be able to multiply?
Yes, sir.
Yes, sir.
Yeah, except you two, anyone, I want one more answer to say yes. Because you have already computed. I know that you will compute. Will others be able to compute? One of you can answer.
Yes, sir.
Very good. Yeah, in case you have difficulties, let me know. Okay, so let us now look for other properties. We said it is a complex number or kind of complex number. So how do you compute the complex conjugate? If you have given simple complex number, how will you compute the complex conjugate? A plus IB.
Minus I.
That's all. So here, what should you think? What do you expect will be the conjugate?
Q0 minus IQ1 minus JQ2 minus Q2.
Negate the vector.
Excellent. Very good. Negate the, you said something. Tell me again. Negate
Vector
the
part.
vector. Excellent. That's correct. Negate the vector part. So if you add the complex number and its conjugate, what will you get? A plus IB plus C plus ID.
2q0.
Real part.
One you get only real part.
Why is the real part?
Okay. No, that is Q plus Q star. What you said is correct. That also is correct. So if you do Q plus Q star, you get 2Q naught. So this is your negate the vector part. So Q plus Q star is 2Q naught. And if you multiply two complex number A plus IB and multiplied by its conjugate A minus IB, what will you get? A plus
square
IB
plus
into
B
A
square.
minus A square plus B square. Will you get the same thing here?
No, sir, not necessarily.
Okay, so let us go back and multiply and see. Use this definition. What will happen to PQ naught and
Those two will get
QP?
cancelled.
Assume, okay, this one?
This is 0.
0 because it's a determinant
Zero.
condition.
So all three are gone. So what will you get here? P naught Q naught is Q naught P naught square or Q naught square, whatever it is. And this one of them was already minus. So that minus will become plus. So what is your answer now?
P square plus mod P
With a
vector.
norm.
Mod P square or something.
Basically P naught square plus Q naught square Q1, sorry, P square Q1 square plus, okay, if it is Q, it is Q naught square plus Q1 square plus Q2 square plus Q3 square. Do you agree?
Yes, sir.
That's so it is good. It has all the properties of complex numbers, right?
So the third point, I think you missed a 2 there, sir.
Pardon me?
So in the third point, you missed a 2 there, sir. Third point. Q
Here.
star equal to 2Q0 minus Q.
Here.
Oh yes, sir. The above third row, sir. Not
No,
sir.
it is
Third
Q
row
vector there.
is just a Q star is Q naught minus Q star. I am
Okay,
just
vector.
defining Q star. I'm defining Q star here. Is it okay?
Yes, sir. Sorry, sir. I didn't see the vector part. Like,
No problem. Sure. So one more thing is, how do you compute inverse of A plus IB?
A minus maybe by square root of A square plus B square.
Very good. A minus IB divided by A square plus B square. So what about inverse
Root
of
of A square plus
quaternion
B
now?
square also.
Pardon me?
It will be root of A square plus B square in the denominator also.
Do you want the root in the denominator?
No, sir, I think it is fine. Not enough. A
So
square plus
A
B
plus
complex
IB
conjugate.
multiplied, yeah, because A plus IB into A minus IB is A square plus B square in the numerator. So
Yes,
denominator should be A square plus B square only. It is actually norm square, right?
Yes, sir.
So what about quaternions now? If you want to compute quaternion inverse, what will you do?
Conjugate by norms.
Norms.
Divided by norm, same thing. So actually everything, whatever you did for complex number, you do the same thing for quaternions. There is only non-commutativity property which is different. So the norm, it is also normed. We saw the definition, no? It is a normed division algebra, non-commutative division algebra. So unit normal, when you say the quaternion will have norm equals to 1. Except in complex numbers, you had 2 components. You now have 4 components. This is one additional thing you have to separately verify, that the norm of 2 complex numbers, if you have a norm of 2 complex numbers, the overall norm of the product is product of the norms. That is true in the complex numbers. If you look at the initial definitions, if you have Z1 equals to R1 times E power I alpha, Z2 equals to R2 times E power I alpha, when you multiply, what do you get? You get R1 into R2 E power I into alpha plus beta. So the second part has norm equals to 1. So therefore, the product of the norms is norm of the products. So that is true in the case of complex numbers. In quaternions also it is true, but you don't have that E power I alpha expression here. So you have to explicitly separately prove it. Okay, so this is an exercise. You have to do it separately. Here there are 4 components. It will be slightly, you have to work out this. Just 4 with 4 components.
Sir,
Any questions until now?
in quaternion, like,
Yeah.
don't you have the relation like conjugate of P and Q equal to Q star into P star?
Conjugate of,
Like PQ star equal to Q star P star.
that also you have. Yes.
So, sir, if we like
That is
directly,
also true. That is also one of the exercise. I did not include it here. Later on, I will be including. Yeah, very good. That is PQ whole star equals to Q star P star, right?
yes, sir. If we have that, then we don't need to verify. Like, we can directly verify this one.
This expression, is it? Actually,
Yes,
yeah, that also you have to separately show. Either show this or show that. Very good. Good point. Okay, so I think I would have dealt with it later on, but yes, that is also true. When you look at composition of operator, you will require the other one also. Yeah, good that you mentioned it. Any other questions or comments?
no, sir.
Okay. So inverse,
Sir,
we all just yes. Did you want to say
sir,
something?
Yes, sir. Sir, in quaternions, don't we have a form like r into e power I theta, like we have in complex?
Yeah, as of now, I cannot imagine. Maybe you should check it out. If you
Can't we
can
just
choose
have like I
something like
theta, J alpha, and K beta or something? In
so
the
basically, we are saying that ijk e power I theta, e power j theta, and e power k theta.
yeah,
E
some
power some vector.
yeah, there'll be different direction.
Can you try that out? If you can get those things, it will be interesting. Okay, I have not seen it, but if you can somehow work out that kind of expression, that is magnitude multiplied by some vector. Actually, e power I theta is only one vector, right?
Yes, sir.
Okay, check it out. Actually, e power I theta is one vector. You need actually a combination of these three, I, j, k.
Sir, I think theta will be the direction cosine here. Then it will hold, sir.
Yeah, that's interesting. Direction cosines are also three, no, with respect to I, j, k.
Yes, sir.
Okay, just check it out. We will think about it. That's a good one. Okay, then the definition of inverse, we just saw that pre and post multiply. This is one way of doing. Basically, Q inverse will become Q star divided by norm square of the Q. So if you have an unit norm for Q, then inverse and the conjugate are same. Inverse and the conjugate are same. This we will be utilizing it for the rotation operation. Okay, so the definition is over. Just like complex numbers, now you know what is a quaternion. We have to see how we can interpret the results of the quaternion. That is, when we multiply, when we add, when we do something. See, it's a four-dimensional quantity. Our promise was we wanted to do something, some kind of rotation in three-dimensional case. So we have to now see how this interpretation can be brought. So how to give geometric meaning to quaternions analogous to complex numbers and 2D plane. For the 2D rotation, if you had vector P, that is A comma B in the 2D plane, and if you wish to rotate it by an angle theta, you simply represent this vector P as A plus IB. Then the rotated vector is given by e power I theta times A plus IB. So e power I theta is a norm complex number with angle theta. So now our difficulty is it's a four-dimensional quantity. Which part should be 3D vector? It can be Q0, Q1, Q2, or Q0, Q2, Q3, or it could be Q0, Q1, Q4. So many possibilities are there, or it can be anything in between. It's a vector space. So you could choose any subspace of the quaternion, three-dimensional subspace as three-dimensional thing. But will it give us the interpretation what we are looking for? So the answer is this one. This has been worked out after long proofs and things like that. But we will simply state the answer that if you set quaternion, that is scalar part of the quaternion as 0, then the set of vectors in which the scalar part is 0 can be thought of as a subset which has one-to-one representation with the three-dimensional system. So let us see. So we will denote it, the 3D vector we can imagine in our mind as 0, Q1, Q2, Q3 as a quaternion. 3D, if you have a normal three-dimensional vector, you are embedding it into a 4-dimensional space. So we also give another name. Some people call it as pure quaternion. Pure quaternion means in which the scalar part is 0. So let Q denotes all the quaternions and Q naught be set of all pure quaternions. Then Q naught is a subspace of Q, or Q naught is subset. Basically, it is already a subset. It has also additional properties of subspace properties. Therefore, it is also a subspace. Complex numbers have one-to-one representation with points in the 2D plane. That is, every complex number can be associated with a point in the 2D plane. So therefore, the product of two complex number is again a complex number. It's again a vector in the 2D plane. So that is why this issue is not there. But however, our difficulty is quaternion is already a subset. So the pure quaternions is a subset of your bigger set, which is Q. But if you multiply two pure quaternions, will you get a pure quaternion? It is something, so our intention is we have to multiply vectors in a 3-dimensional space so that it represents rotation. So we could not directly do it in the 3-dimensional. We indicated that maybe we require this quaternion without proof, we said. And then we embedded the 3-dimensional space in the 4-dimensional space. So now the question is, if I multiply two pure quaternions, which are representing the 3-dimensional vectors now, will you get back the pure quaternion? Only then this rotation interpretation can be thought of. What do you say? Example is, if you simply multiply I into I, both are pure quaternions because real part is 0. You get -1 where real part is not 0. So simply product rule we cannot apply. I into I is -1. So this is ruled out now. So we have to see what are the other possibilities such that we can get the pure quaternion. See, the intention is one of the vector is given to you, that is your 3-dimensional vector, and someone says you have to rotate it by some angle and some axis. So what should be told? Yes.
Sir, instead of constraining it, the 3D vector representing it as a pure quaternion, can't we put a constraint on the norm or something, sir? Like the norm should be some constant.
That also is possible. Your good point is you can also do that. Right now we are exploring one particular case. Okay. Yeah, your point is right. You can try all things. This is the one which gives you the required thing, but we are now going to redefine the product in a different way. But that's a good point. Okay, question is good question. It turns out that this interpretation is the most reasonable interpretation. Okay, what is this? So if you look at the complex number rotation, one of the complex numbers represented the vector at hand, another represented the rotation operator, which is e power I theta. So similarly, here we can think of one quaternion is pure quaternion, which is representing the vector at hand. Another one is some generic quaternion, which is representing the rotation operation. So let us multiply these two and then see whether we will get a pure quaternion. In general, this is not true. So therefore, we have to add some constraint. Let us see what is it. So if P is the operator, like e power I theta, which we are trying to apply on your given vector, which is represented by the pure quaternion Q. Let us multiply it. If you multiply, our intention is we have to get back the pure quaternion. But you notice that vector part of P dot vector part of Q is the one which is going to create this impurity. So therefore, what would be your constraint now?
So I think it is P not Q, sir.
Oh, this one, right? Yeah,
Yes,
this
sir.
is P naught Q, right? There's a mistake here. It's P naught Q. P naught Q. Thank you for the correction. So this expression you have, this is the real part or the scalar part. But our intention is after rotation, we want to think of P into Q as rotation. That is P into vector part of Q as a rotation operation. Therefore, after rotation, we should get one more pure vector. So for that, we would like to impose constraints on the result. The result, when we write down, it shows that there is a scalar part. So what should be the constraint now? The scalar part should be 0. In the above case, when P dot Q is 0, we get P multiplied by Q as pure. So this can be a candidate for rotation. Do you agree?
Yes, sir.
Candidate, you are not told. So let us see what is the consequence. See, what you are saying is, if I change the vector Q, the operator P also will change. You imagine you are given a complex number A plus IB. If you want to rotate by angle theta, will you change e power I theta? If you given A1, B1 and A2, is the operator same?
Yes, sir.
E power I theta is fixed. It is not changing. It is only the operand which is changed. So in this particular case, what we are noticing is the operator is dependent on the operand, because that is not acceptable. Okay. So depending on who the operand is, if you keep on changing the operator, then that doesn't have a meaning to say that it is a rotation operator or something. So you can go back and verify that this does not have the desired interpretation. Moreover, this puts a restriction on the P, which is not desirable. That is, operator, we have to imagine P as the operator e power I theta. Is the constraints on the EPC operator is imposed by the operand. So this is not acceptable. Okay, so double product cannot do the job. See, because it is not commutative, you will say I will multiply Q times P. But here there is only one change that is going to happen. It will be, which will not affect once again, because dot product is commutative. And here you will get Q cross P or something. So whether it is P times vector part of Q or vector part of Q times P, we end up in the same situation where the operator restricted to the operand. So one can go back and verify that this will never have the desired interpretation. A very general desired interpretation cannot be. Basically, double product will not do the job. That is the conclusion. Double product does not have the desired interpretation. In the sense, the geometric interpretation we are talking about. So maybe double does not have triple. Triple in the sense, we should use the operand once and operator twice. So let us assume there are two things which represents the operator, P and R, and your pure quaternion is your Q. So how many possible ways you can get these three possible things getting multiplied? There are 6 possibilities. The PQR, QRP, RPQ, RQP, PRQ, and QPR. These are the 6 possibilities. We have to choose which one will represent the rotation. Look at the case when R times P. See, both are arbitrary now. They are operators. R and P are operators. RP can appear on the left hand side or RP can appear on the right hand side in these two cases. So these two cases are not different from each other. Okay, it's like, see, what is RP? RP is once again representing one more quaternion. RP is representing one more quaternion. So even in this case, it is PR. PR is representing one more quaternion, but we have already seen it is equivalent to the double product case. In the double product case, the quaternion is either appearing on the right side or left side of the given pure quaternion, that is Q. So therefore, these four cases, that is whenever RP is on the right or left, or PR is on the right or left, they are all same as your double product case, which we just now explored. So they will not have the desired interpretation. The only case we have to check now is only two cases. Whenever Q occurs in the center. Is that clear?
Yes, sir.
So the pure quaternion Q appears at the edge in the products, these four, whichever we discussed just now. That is the RP, PR, either appears on the left or the right of the pure quaternion Q, which is representing the vector to be rotated, and the remaining thing is the operator. So since P and R are arbitrary, it is enough to consider only the quantities in which the when P and R appears on the both sides of Q, or Q occurs in the middle. So that's what we say. So let us multiply this PQR and then see what is happening. So our intention is this PQR should give you a pure quaternion. When you are rotating a vector, you should get a vector. So you should get a pure quaternion. So when you multiply these things, let us look at the scalar. This is the expression for the scalar part. If you can go back and compute, okay? So we will not do it now. You can later on verify that if you have P times vector part of Q times R, then the quaternion multiplication will yield the scalar part, which is given here. You can notice that there is R naught P dot Q and P naught R dot Q minus P cross Q dot R. So this quantity should be 0. And setting this to 0 should not be because Q is having certain property. So it should be independent of Q. You can apply constraints on P and R. Okay, P can be related to R or R can be related to P. But you should not have any relation with Q. So that is the way you have to consider what should be R and P such that this expression is 0. We need the scalar or real part to be 0. This is our intention. And one more, additionally, what we are saying is it should not be dependent on the Q. So independent of the Q, what are the minimal set of assumptions you will make on P and R? So if you set a P and R to be 0, okay, this expression will be 0. So that is too much. You should set minimal constraints on P and R such that this quantity is 0. So if you look at this expression, let us consider this first case. Is the statement clear?
Yes, sir. Sir, for rotation, like we are considering 3D rotation, right?
Yeah.
Okay, sir.
You see, right now we are looking at it algebraically only. We have not told how it will become geometry at all. The first requirement in the geometric interpretation is if you assume pure quaternion to be a vector, and whenever you operate on it, it should remain as a pure quaternion. That is the part we are showing. So once we show that we can do that in a reasonable way, we have to see how to interpret as a rotation operation, if it is possible.
Okay,
That's
sir.
the next. So let us check if R naught and P naught are equal. What would happen? If R naught equals to P naught. So that will allow, no, here it is P naught. This is P dot Q and this is R dot Q. Yeah, this will give us this expression. That is, if you set R naught and P naught as equal, then Q also can be taken common out. So P plus R will come in the center. Okay. Is this okay?
Sir, from the above expression, sir, can't we take this is something like P dot R minus P cross R, P vector cross R vector into Q or something like equal to 0.
So you are saying you can simplify this, is it?
Yes, sir.
This
Like,
expression.
yes,
Yeah.
sir.
How will you simplify?
Sir, first, like we can take minus R naught P dot Q in the first expression. The second expression minus P naught R dot Q. And in the third expression, we can interchange the dot product and cross product,
Yeah,
like in
very
triple
good.
product.
Excellent.
And
Yeah,
then we
that is-
can get something like PR minus P cross R, something like that.
Yeah, very good. Actually, that is what we will do now. We will see since Q is contaminating this, I would like to take it outside. Very good. Applying the excellent. Okay, good point. If you apply the vector algebra rules, this Q can be brought outside with a plus sign here. Okay. Yeah, you also try your method, okay, directly, and then show that if we both get the same result. I am doing it in this way, but please try it the way you are doing and let us see if we can get the similar expressions. But ultimately what you said is true, that we have to play around with this cross dot interaction. So from here, can you tell what additional constraint you require? You have P plus R and P cross R. And you
P
want
dot
the
R.
whole expression to be 0.
P
Yeah.
dot R should be 0. Like,
Which one? Do you want P dot R to be 0? Why?
PR minus P dot R should be
It is
0.
actually. Come back again.
PR minus P dot R, something like that, sir.
PR minus
P dot R.
P dot R.
Yes, sir.
PR. PR or QR? PR minus P dot R.
So P naught
So if
square
you
plus
set vector,
P naught square
pardon me?
plus P dot. So P naught square plus P dot R is equal to 0 means we'll get so.
P come P
P naught square
once again.
plus P dot R or P naught R naught plus P dot R. If we set it to 0, we might get something.
P naught square minus P dot R
Plus P dot R. If you
plus P dot R.
put that equal to 0.
Okay, maybe
Then it is
yes.
what I'm thinking
Probably.
is like PR is equal to.
So the simpler I am looking at it this way, if you simply set from this expression, see basically you want left this term to be 0, this term to be 0. If you set R equals to minus P, probably you may get whatever you said. Just check it out. If R is
Yes, sir.
minus P, then this is 0, this is 0. Is your expression also same? P naught R minus.
Mine is a bit more general, sir.
Hmm.
Like, but I don't know if that will work though.
No, will it give the same result? Just check. It may be close to that. No, I think that may not be. No,
No, sir.
that may be slightly more restrictive. So this one is one of the simplest constraint you can apply. So we will discuss this once again next class. I'm just stopping it. So basically what we are saying is if R is minus P, We have already told R and P naught are equal. Basically, we are saying that R is nothing but P star. So what we have is PQ P star. And if you have RQP, it is same as this only. It is P star QP. So it is basically we have to check whether PQ P star in the center you have Q vector part of Q. Okay. If you are given a quaternion, and if on the left and right you multiply by the conjugates of a general quaternion, you get the pure quaternion back. If you have a pure quaternion and on the left and right you multiply by an arbitrary quaternion and its conjugate, you get back the pure quaternion. Okay, I will stop the class here. I think you have other classes. We will discuss this in the next class. Thank you all and have a good day. I will be here and if you have any questions.
Thank you, sir.
Yes. The class is over. I think you have other classes. That's why I cannot already over.